In previous video, we saw that the waveform of Godunov's method. So we further expand that idea to calculate the waveform in terms of matrices. So let me just remind you what we have done earlier. We had a numerical method which was generalized as minus delta t by delta x a plus delta q I minus 1 half plus a negative delta q I plus 1 half. So that was the equation that we derived earlier. Now suppose that we have a equation a partial q by partial x is equal to 0. Then we can write the waveform as I minus 1 half is equal to alpha p I r of p. Since all the values may be coming from left to right for the cell I. So for example, if we have I minus 1 half and we have I plus 1 half, so this is cell number I, this is cell number I, and at this cell number I, thus we have alpha p I, and for that wave we have RP. So we are calculating the wave at each cell. The remember RP is the eigenvector and lambda p is the eigenvalue. Then we can write lambda, or some people call it omega. So this is the lambda. Lambda plus have all the waves which has positive speed, lambda 2 positive, and then we have lambda m positive, and we also have lambda or omega with negative eigenvalues. Lambda 1 is negative, lambda 2 is negative, and then we have lambda m is negative over here. Okay, from our earlier lectures and also from linear algebra, we know that if we have a matrix R and we also have lambda and there is an inverse of that R, then the output matrix A, the output matrix is A, which contains all the eigenvalues from this lambda. In our case, if this lambda contains all the positive eigenvalues, then we also have all the values in A containing positive speed or positive values. Similarly, if we have R, which is a matrix containing all the eigenvectors as a column, and omega, then we have negative R minus, and then we have A negative. Okay. You can see that by adding A plus plus A minus, what we get, we just add these two terms, R omega plus R minus plus R omega minus R minus 1. From here, it can be written as R omega plus omega minus r minus 1. So we can write it, for example, if I multiply this r with omega plus and r inverse on the right, then r omega inverse r inverse. So this is equivalent to the above expressions. And from here, suppose this omega plus and omega minus is actually omega. Suppose that we have all the eigenvalues positive, and we also all the eigenvalues maybe some are negative and some are positive. Okay, let me just write it again. Omega plus omega minus. Suppose that we have 2 and 0. Only one eigenvalue is positive, and then we have another eigenvalue is negative, which will arrive in which can be placed in this matrix. When we add these two, then we have 2 0 minus 2. So in this one matrix we have positive eigenvalues and the negative eigenvalues. So this can be written as omega. So we can write omega or lambda or omega r minus 1, and a this will be equal to a when we have lambda which contains positive and negative eigenvalues, then we get a. When we have eigenvalues, the matrix which contains positive speed, then we have a plus. So it means that a plus and a minus add up to make the matrix A. Okay, now we can also write this as follows. Suppose we have A plus delta Q I minus 1/2. A plus means we can write R omega positive omega R inverse. This is the definition of similarity matrices. And delta Q I minus 1/2 means we have Qi minus Qi minus 1. Let me just remind you what is delta Q I minus 1/2. It means that we have I minus 1/2. On the left we have Qi minus 1, and on the right we have Qi. So delta Qi minus 1/2 means that we take the forward value and take a difference from Qi minus 1. Okay, so we just need to solve the right hand side. We have R omega R inverse Qi minus Qi minus 1. So we remember that, or there should be plus sign, and we remember that R inverse Qi will be equal to some quantity that I will write it over here. What was that? We already saw that the Qi minus Qi minus 1 was equal to alpha and some R, right? So when we, for example, I write again Qi minus 1, there was a jump, so we can write R alpha. Then we take inverse Qi minus 1, so this becomes alpha. So we can replace this R inverse Qi minus 1 with alpha. So this quantity becomes R omega plus, and this quantity becomes alpha I minus, where we are calculating as I minus 1/2. So we have A plus delta q I minus 1 half is equal to r omega plus alpha I minus 1 by 2. So we have P is equal to 1 to m. This R is a matrix. Now I want to write this as a summation form. R is just the matrix which contains all the eigenvectors, and omega positive is lambda P plus alpha P I minus 1 half, and then we have RP. This RP is due to the matrix R. R actually contains all the eigenvectors R1, R2, R3, so on. So this R is small r is due to that capital R, which is a matrix. Omega positive has the positive speeds, and alpha I minus 1 half is already there. We just write it in the waveform. So similarly, we can also write A minus delta Q I minus 1 half is equal to, that will be R omega negative, R inverse, and we have the same qi minus 1, and this can be written as r omega inverse alpha I minus 1 by 2, and in the waveform we have p is equal to 1 to m lambda p minus alpha p I minus 1 by 2 r p, and then we have a negative delta q I minus 1 half. So it was the same that we did earlier. Okay, now let me just write the Riemann problem for the Godunov's method x at x is equal to xi minus 1 half. Suppose we have qi minus 1 half value, and that value can be obtained as qi minus 1 qi. Let me just talk about that with the help of the averages. From the average formula, we had qn and 1 over delta x, xi minus 1 half, and xi plus 1 half. Then we have qxt and dx. So we saw that if we could write this q as a constant, q will be equal to q constant value or q whatever the static value, then we have a Godunov's method. So suppose that we have this qi minus 1 half is static, or maybe some arrow over here which shows that we are working with Godunov's method for the Riemann problem. And this on I minus 1 half we have I and I minus 1 value, and this is the q arrow that is for the Godunov's method. And suppose that the information is traveling from qi minus 1. There is only one way where the information can travel, but if we have something else that is coming from the right side, let me just write it for you. On I minus 1 half, the information can travel if there is only information that is traveling from the left side. On the left side, we have I minus 1. If the information is only coming from I minus 1, from the variable I minus 1, and there is nothing on the right hand side, then this is enough. But suppose that if we have some information traveling from the right as well on the cell I minus 1 half, then it means that we need to add some summation which shows that the wave that is traveling from right to left has a speed less than 0, and we can write the waveform of that speed, that wave. So this will become plus p lambda p is less than 0 and wp I minus 1 half. Okay, and what we do, we write the same for this was for a quantity q. Suppose that, what does this mean? Partial q by partial t partial by partial x u bar q is equal to 0. Here the variable q is a solution, but the flux is u bar q, so the flux is u bar q. Okay. Similarly, we also write this qi minus 1 half only for the variable. But if we want to write this for the flux can be written as, for example, q arrow means that we are working with Godunov's method, and we also have q, and this is q arrow I minus 1 half. So the flux at I minus 1 half will be equal to a q I minus 1 plus p lambda p is less than 0, and we also have a wp I minus 1 half. So essentially what we did, we multiplied the maybe I can show you over here first. Suppose that we have the same equation, which is the advection equation for the scalar form. If q is the solution, how can you get the flux? Simply multiply that with u bar. Similarly, if we have a solution for the variable, we can multiply that with a everywhere and we get the flux. That's what we did over here. So in the summation form, this is only shows that we have all the information for the flux coming from the negative speed, the wave from right to left. If it is written as fn I minus 1 half aq I minus 1 half plus p is 1 to m, then we have lambda p minus wp I minus 1 by 2. Okay, this was the form that we use for the component form. Here we have a matrix. Here we have a matrix, but here we have the component of that matrices. Okay. Similarly, if we want to see the information on this qi minus 1 half is coming from the I, from the right hand side. So we can write q arrow I minus 1 half, which shows that Godunov's qi information is coming from qi. It should be subtracted. In that case, it will be added to the qi minus 1. But for lambda p greater than 0, it should be subtracted. P lambda p greater than 0, wp I minus 1 by 2. So the flux will be Fn I minus 1 half will be equal to aqi minus p 1 to m lambda p plus wp I minus 1 by 2. So the flux can be written as, for I plus 1 half, Fn I plus 1 half aqi plus p is 1 to m lambda p negative wp I plus 1 half, so on and so forth. That's how we write the fluxes. So the numerical method is qn plus 1i qni minus delta t by delta x fni plus 1 half minus fni minus 1 half, and we have, for example, qn I minus delta t by delta x. So we replace this I plus 1 half with the values. And we have, for example, P is 1 to M, lambda P negative, WP I plus 1 half minus P is 1 to M, lambda P plus WP I minus 1 half. That's how we write the fluxes. Okay, where you can see that the AQI will be cancelled out. For example, if we have probably added this AQ over here, that AQI and that AQI will be cancelled out. That's why the only survived terms we have is this right hand side and this term over here, which is put it over here. Okay, so in general we can write for partial q by partial t plus partial f by partial x is equal to 0, we can write f n I minus 1 half is equal to f of q I minus 1 plus p is equal to 1 to m lambda p with negative speed wp I minus 1 half, and that will be equal to f of q I minus 1, and we can write it as a minus delta q I minus 1 half. Similarly, fn I minus 1 by 2, and we also have f of qi. Remember that there is a qi minus 1 and there is qi minus p 1 to m, and we have lambda p plus wp I minus 1 half, and this can be written as f of qi a plus delta q I minus 1 half. So these will be the fluxes. So this was all the discussion of the waveform of Godunov's method. So we covered this topic and we actually uh, finished this topic over here. In the next video, I will talk about the flux difference and flux splitting method, and maybe I will also talk about the Rose method as well. Thank you for watching.